Hello, I am very happy to present my postdoc project, Data-Driven Design for Climate Action. My name is Haluk, and I am advised by Francesco and Yolanda, both associate professors at KTH, and we're all affiliated with the KTH Climate Action Center. Part of the motivation for this project is that design has a very large effect on how functions are satisfied throughout the life cycle, but also how carbon emissions result from decisions that are made in the material selection all the way through use, manufacturing, and recirculation. There's very little feedback for the designer at the early stage of design. So one of the goals of this project is how can data be used to drive more sustainable decision-making in the design. And if we look at the relationship between the design and manufacturing domains, one really great example of sustainable manufacturing is that of a circular economy, where we have one upstream manufacturing process that results in some sort of byproduct or waste that could then be used as an input to reduce the material consumption for the downstream manufacturing system. This is a great sustainable system in terms of producing products. However, it does require a lot of investment in order to scientifically find exactly how to use these byproducts in a way that will still satisfy the intended functions of the eventual product. Also, coupled systems then are very vulnerable to disruption because they are so tied and so dependent on these byproducts from the upstream. A great technology that we've used in other cases of designing manufacturing to extract requirements is that of AI language modeling. Language is an extremely rich form of communication, but it's not represented for machines in the same way that tabular or image graphical data is represented. So language modeling provides us a way of representing requirements, process variables, design parameters in a way that's quantitative for computation. And we can use these types of models to represent and measure similarity between different functions that need to be satisfied. This project proposes a digital twin concept based on modeling how functions are identified and addressed throughout the manufacturing process. Essentially, if we can address how a change that's made very early on in the manufacturing system propagates down to the next downstream manufacturing system, then we can facilitate better bidirectional communication between the decision makers at both ends of the processes so that we never interrupt circularity despite disruptions due to change and adjustments. We performed a case study on circular bioplastics. And so this was a case where byproducts from the agro-food industries, so producing potatoes, result in these starch byproducts that can then be used to make absorbent materials, such as used in sanitary products, such as diapers. And so then this type of a system is great because it reduces the amount of plastics that are being used, and it also reduces the waste from the agro-food industry. It's very dependent, though, on the precise chemical composition of these upstream byproducts. And so in this case, when the upstream byproducts are changed due to an adjustment from a solid state to a liquid, we can then use our functional digital twin to estimate how this adjustment will propagate from the upstream, and we can alert the downstream processes that are vulnerable to this change. This is a visualization showing how this measure of functional similarity can be highlighted and then used to alert downstream decision makers. So thank you for listening to this very short summary, and we hope to see you at the poster fair. So thank you so much.